In this video, we are going to talk about exercise number 6, experiments on carboxylic acids. Carboxylic acids contain the carboxyl functional group, which combines the carbonyl group of aldehydes and ketones with the hydroxyl group of alcohols and phenols. This combination then causes the physical and chemical characteristics or properties of the carbonyl and hydroxyl groups to influence each other. And as a result, the properties of the hydroxyl group in the carboxylic acids differ significantly from those in alcohols or phenols, and the properties of the carbonyl group differ from those in aldehydes or ketones. A hydroxy group directly attached to a carbonyl group, and the interaction between them affects the reaction of each. Thus, the polarity of the OH bond is greatly increased, and the tendency to release a proton or acidity is higher than alcohols or even phenols. Direct addition of nucleophiles to the carbonyl group is also less likely. However, the carbonyl oxygen atom is directly protonated in the presence of strong mineral acid, and the resulting organic cations can then combine with a nucleophile to form a new bond at the carbon atom. Functional derivatives of carboxylic acids are compounds which hydrolyze to their salts. Included are the following compounds: acid anhydride, acid halides, nitriles, esters, and amides. The objectives of this exercise is to determine the physical and chemical characteristics of carboxylic acids, to observe and rank the solubility, alkalinity, reversibility, and acidity of selected carboxylic acids, and to observe the reactions of acid anhydrides and amides and the preparation of esters.
This is the schematic diagram number 1, the solubility test. First, prepare the following test compounds: glacial acetic acid, propionic acid, butyric acid, salicylic acid, benzoic acid, and citric acid. Second, into each of the 4 empty test tubes, add gml of distilled water. Third, add a small amount, 1 ml for liquid samples, 1 grams if solid, of each carboxylic acid into separate test tubes. Fourth, shake each test tube and identify which acid is water-soluble. Fifth, for acids that did not dissolve in water, add 40% sodium hydroxide solution dropwise. Sixth, shake after each addition of drop until dissolution. Seventh, determine the number of drops of sodium hydroxide needed to dissolve the acid. And lastly, add 1 drop of concentrated sulfuric acid and observe if the carboxylic acid precipitates out of the solution.
In this experiment on acidity of carboxylic acids, we prepared 0.05 moles per liter solutions of glacial acetic acid, butyric acid, salicylic acid, benzoic acid, and citric acid. We then added 3 milliliters of each solution to each test tubes and determined their pH using the pH paper. The pH values were then recorded on the datasheet. Next, we added 3 drops of phenolphthalein indicator to each test tube. We titrated each solution with 0.10 m of sodium hydroxide solution dropwise, shaking the tube after each drop, and stop when the mixture turned light pink. We then recorded the number of drops it takes or needed to neutralize each acid. Finally, we ranked the carboxylic acids from most acidic to least acidic based on the number of drops required for neutralization.
For the third experiment, which involves acid anhydrides, I will be explaining the procedure. First is to prepare 3 test tubes labeled as A, B, and C and add the following chemicals to the corresponding test tube. For test tube A, add 5 ml distilled water. For test tube B, add 1 ml alcohol. And for test tube C, add 1 ml aniline. Test tube B and C is placed in an ice water bath. Next is to test tube A, and doing that is to add 1 ml acetic anhydride and place in a warm water bath for 3 minutes. Next is to test the solution on blue litmus paper and note the color. Next is to add 1 ml acetic anhydride and 1 ml sodium hydroxide solution dropwise in test tubes B and C. After that is to shake the mixture and observe for the formation of products. And lastly is to record observation.
And I will be presenting the schematic diagram of the experiment number 4, reactions of amides. So first is we will set up 2 test tubes and assign labels to them. One test tube will be labeled as D and the other one will be labeled as E. Next is to add 0.5 grams of acetamide to both test tubes. For the test tube labeled as D, we will add 5 ml of sodium hydroxide, while for the test tube labeled as E, we will add 2 ml of dilute sulfuric acid. And then, we will place both of these test tubes in a water bath and allow them to release vapors. And finally, we will observe and record the odor of the vapors produced or forming from each test tubes.
For Experiment 5, Preparation for Esters. This experiment aims to prepare esters through the reaction of various carboxylic acids and alcohols in a process called esterification. This experiment condenses into a series of steps. First, label 5 test tube for each acid: acetic, butyric, benzoic, salicylic, and propionic. Next, add 2 ml of the acid or 0.5 gram if solid to each tube. Next, add 3 drops of 6 moles sulfuric acid solution to each test tube. Next, identify the specific alcohol, 2 ml, that needs to be added to each test tube containing a different acid. Refers to this to determine the specific alcohol that needs to be added to each acid. After place all 5 test tubes in a warm water bath for 3 to 5 minutes. And then, dip clean filter papers strips into each mixture. Next, gently fan the moistened strips to identify the odor from provided options. Is it either plastic bubble, wintergreen, apple, pear or apricot, nut or cherry. After record the perceived odor for each test tube.
And I am going to discuss the theoretical result in the first experiment, titled as the solubility of carboxylic acid in water. So for the first compound, we have the glacial acetic acid, which showed solubility in water. So this is due to the ability of the acetic acid to form hydrogen bonds with water molecules. For the second compound, which is the salicylic acid, which showed insolubility in water. So this is due to the presence of a non-polar aromatic ring, which hinders its overall ability to hydrogen bond with water molecules. So the hydroxyl group attached to the benzene ring also forms intramolecular hydrogen bonds, reducing its interaction with water. So moving on to the third compound, which is the butyric acid, which showed solubility in the water. So butyric acid has a longer carbon chain than acetic acid, which makes it less polar and reduces its solubility in water. However, it still has a carboxyl group capable of hydrogen bonding, making it moderately soluble, so it's still considered soluble in water. So moving on to benzoic acid, which showed insolubility in water. This is similar to salicylic acid. Benzoic acid has a limited solubility in water due to the presence of a non-polar aromatic ring that does not interact favorably with water molecules. So lastly, we have the citric acid, which showed solubility in water. So citric acid is highly soluble in water due to its 3 carboxyl groups and 1 hydroxyl group, all of which can form strong hydrogen bonds with water molecules. This makes citric acid highly polar and readily soluble in water. Now proceeding to the solubility of the test compounds with dropwise of 40% of the sodium hydroxide. So take note that the glacial acetic acid, butyric acid, as well as our citric acid are no longer available due to its solubility in water. So proceeding to the salicylic acid, so salicylic acid required 1 drop of 40% of the sodium hydroxide to dissolve, while the benzoic acid required 4 drops of the sodium hydroxide to dissolve. So now proceeding to the reversibility of the test compounds. So take note that this is all a theory, which means that it could still be changed based on or varying on the results of the experiment. So all of the test compounds, according to my research, has shown a positive reversibility, meaning that it could still be reversed, or the original form can still be obtained, varying on the steps that you are going to apply.
And I will be reporting about the theoretical experiment on the acidity of carboxylic acids. In this theoretical experiment, it aims to determine the relative acidity of various carboxylic acids by measuring their pH level and the number of drops of sodium hydroxide, or we also call as NaOH, needed to neutralize them. Next, we have the benzoic acid. pH is 2.9, 12 drops, and acidity rank is number 4. Third, we have the butyric acid. pH is 2.8. It takes 13 drops for neutralization. Acidity ranked is in number 5. Next, we have the citric acid. pH is 2.2, 18 drops. Acidity ranked is in number 1. Citric acid has 3 carboxyl groups capable of donating protons. Citric acid exhibits heightened acidity, leading to notably low pH and a pronounced sourness. And lastly, we have salicylic acid. pH is 2.5, 14 drops. Acidity ranked is 2 acid. Overall, this experiment highlights the diverse factors influencing the acidity of carboxylic acids, including molecular structure and functional groups, providing a deeper understanding of their chemical properties.